Hello, and thank you for your interest in our research. My name is Juan, and I represent the Australian Research Centre for Interactive and Virtual Environments. Today, I will go through the research project Smart Pipette, Elevating Laboratory Performance with Tactile Authenticity and Real-Time Feedback. So what is the motivation behind this research? In a typical science degree, students have limited access to lab equipment, which means limited hands-on practice time. And those who study remotely have no access at all to lab equipment, which impacts their job readiness. Employers often need to retrain graduates, which is not ideal, as they are expected to be fully prepared. Custom haptic devices have demonstrated to be effective in training applications in surgery and welding, enabling unsupervised hands-on training and teaching of complex tasks. Our team has performed a background review around virtual laboratory training, in which a total of 47 virtual laboratories were identified. We found that 7 out of the 47 initiatives include a haptic device. 30 are part of a research project. 11 are commercial initiatives, and 6 are free or open source apps. It seems the number of active initiatives has been increasing over time, which shows a growing interest in virtual laboratory training. Most of the virtual laboratories we found use a two-dimensional display, such as a computer or a smartphone. Less than half of the simulations use a virtual reality headset. For this reason, we decided to use a computer screen on our first user study, and we will add an augmented reality headset in a follow-up study. Our main interest for this user study is to evaluate the viability of custom haptics for science learning. Consider the air displacement pipettes. This tool will be used as our domain example for studying hands skill training off campus. Learning how to use a pipette is a task that requires hand dexterity and some level of muscle memory. It is definitely more complicated than it looks. Our research gap is that current virtual laboratories focus more on theoretical aspects with limited exploration of tactile authenticity to enhance hands-on skill performance in unsupervised and distant learning. Our team created a proof of concept using a real micropipette with added sensors. We then developed a hand controller in the shape of a pipette, which was connected to an Arduino using a repurposed Ethernet cable. Finally, we developed our smart pipette hardware, which has a wireless handheld tool and a simulated sample tube rack. The first step was designing the 3D printed case, which is composed of 5 different printed pieces for the hand controller. In addition to the 3D printed parts, we use a metal spring and a piece of metal brass tubing. The sample box has a body and a lid. The lid has 4 holes to access pressure sensors. Tactile authenticity is a key concept in this research. It means that the training tool is similar in how it operates, its shape, its weight, and overall feel to the actual tool you want to train. The hypothesis of improved training when the training tool closely mimics the original is supported by Hamadani et al. And Levac et al. The most critical aspect of our design was replicating the double plunger mechanism of a micropipette. This was accomplished by using a potentiometer with a spring return slider and then adding another spring around it. The small 3D printed ring holds the spring in place until the plunger reaches the first stop. Let me show you. Like so. Continued pressure will then activate the second stop. Just like in a typical micropipette. All 3D printable files and schematics are publicly available on the Wearables Computer Lab's GitHub account. The main metric in our user study is performance. This is important because we found that current research is mostly focused on measuring user engagement, perceived learning, and system usability. But there seems to be a research gap in measuring actual performance after virtual training for science tools. The image to the left shows the training simulation, and the image to the right shows the subsequent evaluation participants underwent. For a control condition, we chose an Oculus Quest hand controller and a number keypad. This is off-the-shelf hardware, which is currently available. The current controller was chosen as it is held mid-air, similar to a micropipette. This slide shows the two conditions side by side. Please note that both conditions use the same computer simulation. This training was self-paced and took on average 16.5 minutes to complete. After training, participants performed a pipetting evaluation. It consisted of delivering 15 volumes of liquid with a real pipette. The volumes were measured on a precision scale to assess for sample accuracy. 5 samples were of 50 microliters, 5 samples of 100 microliters, and 5 samples of 150 microliters, and the orders were counterbalanced. We then calculated precision and accuracy for the samples. We found significant differences between conditions in 5 out of 6 metrics. Note that outliers were included in statistical analysis. When looking at overall pipetting errors, we found that participants training with the off-the-shelf hardware make more errors compared to those training with the smart pipette. Then looking at individual errors, 4 out of 8 errors had significant differences between conditions. These specific errors were not holding the pipette in a vertical position, not starting the aspiration with the plunger at the first stop, releasing the plunger too fast during aspiration, and removing the tip from the sample too fast. No significant differences in cognitive load were found between conditions. However, there was a noticeable difference in the confidence level question between conditions. Even though it did not quite reach significance with a p-value of 0.051, there seems to be a slightly higher confidence level on students who trained with the smart pipette. When looking at the system usability scores, the training tools seem to have acceptable levels of usability regardless of the hardware condition. In summary, we found increased accuracy and fewer errors when training with our custom haptic, while we found equivalent system usability and cognitive load scores. Therefore, we believe Smart Pipette could be a viable approach for distant science learning. The preprint for our paper is now available at IEEE Transactions on Visualizations and Computer Graphics. Thank you for your time.